Okay,
what it's going to be about. So first I will give you a bit of motivation about the problem I've been working on and kind of give the scope of what we can do in this hands-on tutorial today. So histological sections, most of you are probably aware, they're like thin sections of human brain tissue which are cell body stained after slicing them and then imaged at a resolution of 20 to 1 micrometer per pixel. This results in images like this you can see here on the right-hand side. These images are actually quite high resolution, so you can really zoom into different parts of the cortex here and distinguish individual neurons in the cortex. And what we can also appreciate on these bigger extracts here on the side is that the laminar structure of the cortex changes throughout different parts in the cortex. And this is what constitutes, by definition, the differences between two cytoarchitectonic brain areas. And these are the brain areas that we are at my institute at the INM1 and the Research Center Jülich that we are particularly interested in. And if you study these structural areas, this gives you, for example, quite a good idea of the inter-individual variability. So what we did here is we studied the two same areas in 10 different brains, and you can really appreciate the different sizes and shapes of the areas in each individual subject. In addition, what we are doing is we're building this probabilistic atlas of these brain areas. And this then allows the allocation of other data to these structurally well-defined entities. So this sounds all very good. However, it's quite time-consuming to segment these cortical areas by hand because you have to analyze each individual tissue section by hand, and this takes a long time. So this is what I've been working on in the last couple of years to make it to give you a very coarse overview. I have trained a convolutional neural network on the 2D high-resolution tissue sections, and I've trained it to segment areas in this tissue section. That sounds very easy if I put it like that. However, it's a bit more involved, and there's actually a lot of technical difficulties that you run into. You're very welcome to check out our related publications that I put down here on this subject, how we precisely started to solve this problem. I'm not going to talk about these models today because I would like to get you started on training your own convolutional neural network for the segmentation of histological sections. So in this tutorial, I would like to use the 20 micrometer data of the BigBrain. The BigBrain is a publicly available brain volume that has been 3D reconstructed, and every section of the BigBrain is available in a 20 micrometer resolution. The reason why I'm using the 20 micrometer sections here as opposed to 1 micrometer resolution sections is just that if you have a 1 micrometer resolution section, it gets too large to process in an interactive setting like this. I couldn't do it in a Jupyter notebook really because you need a high-end GPU cluster. You have all sorts of problems when trying to even view a 1 micrometer section just because it's several gigabytes large. So this is why I'll be using the 20 micrometer resolution in this tutorial here. So the first task I wanted to train the networks on is the task of gray-white meta segmentation. This is just an easier task than doing area segmentation really, and it's a good use case for testing architectures and different parameters and so on, just because the networks tend to converge when training on gray-white meta segmentation. In addition, we need a lot less training data and have shorter training times, so this makes it a good use case for actually training some networks here in these 40 minutes. And in addition, it's an important task for pre-processing and pre-training, for example, more complex area segmentation models. So it's a good idea to start with something easy where you can easily gauge how well the network is actually doing. But as a second task, I will be showing you the segmentation of area V1, which is the primary visual cortex. And this area has a quite distinctive structure. You have this stripe of generi, which is also visible on the 20 micrometer data. So that means it's actually quite an easier cortical area to recognize. However, it's still a much harder task than gray-white matter segmentation. And we'll see in the course of this tutorial what we need to do in order to adapt the networks to work on that. Both of these ground truth data sets for the gray-white matter segmentation and for the V1 segmentation are publicly available as well. The gray-white matter segmentation comes from a segmented volume of the BigBrain, which is also available on the FTP server where you can find the BigBrain. And the V1 segmentation has recently been made available in the HBP project. So it has like this DOI here, and you can download it from the web pages of the Human Brain project. Okay, so these were my introductory slides. Let's jump over to the notebook. So as earlier, you can find the link to my notebook on our website here. So just click on, where am I here? On the notebook link, and it should open up here. Yeah, you really should be connected to a GPU runtime this time around, because training on CPUs will take over an hour to even train the simplest model here. So what we'll be doing first is we will, download some scripts that I provided to calculate the receptive field of the neural network, and then just import some Python libraries that we need. We will be using Keras as well, as in the earlier presentations. So we are doing that. And now let's download some data that I prepared. So I told you all this data is publicly available, but to make things a bit easier here is I created this zip file in advance, which contains training and testing data for the networks. So let's look at what we just downloaded here. So execute this next cell, and we see I just did an ls. That doesn't look too good. Let's see. Unzip cannot find the directory. That seems great. I'll just try and execute this again. So it says it cannot unzip the file. I've never had this problem, but you know, this is the thing with live presentations. I will just be jumping over to my personal saved notebook. I will check right after the presentation what the problem with this is here right now. Maybe it's the internet connection, I don't really know. I will just be jumping over right to my personal notebook that I prepared just in case. So this is running on my laptop here now. I'm sorry about this if it isn't working for you. Just try to follow along. You can still have a look at the code. I will try and see what happened with the data here. So let's execute this notebook then. I have already downloaded the data, so I'm not going to execute that again. So let's have a look at what we should have downloaded. So we have a bunch of NPZ files here, which contain training and validation data sets for the gray-white matter segmentation and for the V1 segmentation. In addition, we have a test folder down here containing histological images of the BigBrain, these files here, then containing V1 segmented files and gray-white matter segmentations. So if we now have a look at these files in the test folder, there we go. So we see we have the histological sections of the BigBrain. We have gray-white matter segmentations consisting of 3 classes, and we have the V1 segmentations consisting of 2 classes only. Okay, so we ideally now have our data. I'm really sorry that it didn't work online there. And we are all set for doing the gray-white matter segmentation. So first, let's have a look at the size of one of these sections. And you see it's 5,700 times to 6,500 pixels. So it's really a very large image. And in fact, it's so large that it doesn't really fit on the GPU. So we can't really use one of these images as one training data point for training the networks. But what instead we need to do is we need to crop small patches from these histological images and use those for training the networks. And now, of course, there are several choices that we have to make when cropping small images from these large images. And the first question is, how large should these patches be? And there's always some trade-off between efficiency, that means larger images, and variability of the data, that means many small images showing different parts of the brain. In addition, you need to make the input patches large enough to show relevant context to actually solve the problem that you're trying to solve. And in addition, the minimal input size of your network may be limited by the choice of network architecture. So you need to check that before fixing just the patch size that you're inputting. I chose a patch size of 268 times 268 here, which shows about 5 times 5 millimeter of tissue. So that should be sufficient to do the gray-white matter segmentation, really. The next question that you might have is how many patches should we sample from these data? And there really the answer is as many as possible. I computed the patches beforehand here and I saved them in these NPZ files because that's reproducible and faster. However, it's also possible to do random sampling during the training process. And this will then increase the variability of your training data. So you might have a process on the CPU always live sampling random patches from your data, and then a process on the GPU actually training on this data. This is a bit more involved, and I chose to not do this here to not complicate matters further. And maybe the most important question is, how should we sample the patches? That is, where should they be coming from? And they should really be sampled from the interesting parts of the image. So if you consider this section here, you can see that we have a lot of background, a lot of white on these images. So if we were to sample just randomly, random coordinates from this image here, we would get a lot of patches containing just white. And that's not very interesting. What we really want to have in the end is, if we want to train on these three classes, background, white matter, and gray matter, we want to have a data set that represents each of these classes equally. So this is what I did when with sampling the data set. I did a weighted random sample, and I calculated the weights in such a way that in the end, I have an equal distribution of all of these three classes. I prepared these cropped train and validation data sets in advance. I have linked here the notebook that I used for this. This is also available in my GitHub, where this tutorial is also living. So you're welcome to click on that link and have a look at how I created those data sets. For now, let's just load one. Let's load the train gray-white matter segmentation and the validation associated validation data set. This returns a list of patches that we train on and of corresponding labels. So I've defined a function to plot these here. So this just plots the first num examples of the images and labels. And we see that I created a data set only containing 500 training patches. This is not a lot, and you could easily create more patches from the data that we have available. I just wanted to choose a small set of samples in order to be able to train the networks here. And we have 20 validation images, which is also not very much. So the patches look like this. So they just show small parts of the section, and then we have these associated labels with it. So we have the three classes. And you see that this segmentation is a bit coarse because it was calculated from a 200 micrometer resolution volume and just upsampled to 20 micrometer. So this is why you see the steps here. It should do fine for training the networks though. So, and this is the validation set. Okay, so we have our data in place. Now let's talk a bit about the architecture that we need to use for segmentation. For segmentation, you should use a fully convolutional network. That is, you shouldn't use any fully connected layers in the network. And that's because this will allow us to predict on larger images than we train on. One very common architecture is the UNet architecture. So this is the original network here from Ronneberger in 2015. And you see we have kind of these two branches. We have a downsampling branch, which reduces the resolution of the images. And then we have an upsampling branch, which increases the resolution again. And in the middle here, we have these copy connections, which concatenate activations from the downsampling branch with activations from the upsampling branch. And the reasoning for that is that the resulting output segmentation can be more fine-grained than if you were to downsample and then upsample again, because you lose a lot of spatial resolution down here. So usually the original UNet architecture is quite a good starting point for training your networks. However, you might want to adapt it to your specific needs. So for example, you might want to make it even deeper, kind of add more, go further down in the U here, or make it a bit wider, that is, use more convolutions per block here, or use more convolutional filters, or whatever you can think of, really. One important point I wanted to make here is for the specific problem of segmentation, especially if we want to, in the end, segment really large images, we need to use valid convolutions. That is important so imagine if we wanted to segment a very, very large histological section that doesn't fit in the GPU in one chunk. So what we need to do is we need to cut it in several smaller sized images and predict on those, and then put the smaller sized images back together into a large image. And if we were to use a convolution with padding, we've actually seen this figure before in the presentations. So if we were to use the padding, you can kind of see here, kind of inventing new pixels right at the border of the image, then we would get artifacts in between the smaller sized images that we needed to predict on. And since we want to avoid that, I'll be using these valid convolutions here. However, this has the effect, of course, that your output will be a bit smaller than the input. And you need to be aware of that. And actually, for this reason here, I'm defining two crop-to-shape functions. One is for cropping tensors to a certain shape, and one is for cropping arrays to a certain shape, because we need that later in the network definition. For defining the UNet, I have defined a handy function here which takes an input tensor, which can be any shape you like, and I give it the number of classes, which will just be the number of softmax outputs of the network. And note here that in this definition, I'm using the crop-to-shape tensor function here before concatenating the activations from the downsampling branch to the upsampling branch, because the sizes are slightly different due to the use of these valid convolutions. So let's execute that cell, which creates our model. And in the model summary, you can see we have an input size of 268, and we have, very down at the bottom, we have an output size of 84. So we really reduce the output size a bit, but it's all for the good of having nice, seamless predictions in the end. One interesting thing I always like to have a look at when creating a neural network architecture is its receptor field. So we have this fully convolutional network. We can input any size we like. However, a prediction for an output pixel at a certain position will always be based on a fixed width window of pixels on the input image. And this width of the window is what we call the receptor field of the neural network. And this is determined actually by the neural network architecture. So for example, if you have a 2x2 pooling layer, you will increase the receptor field by a factor of 2, because you're always summarizing 2 pixels in one. If you have a 3x3 convolution, for example, the receptor field is increased by the amount 2. And you can calculate this easily by going from the output layer back through the computational graph to the input layer, and just doing the arithmetics you need to do for the kind of layer you're at right now. This is a script contained in the receptorfield.py scripts, because it's actually a bit involved for the UNet, because we have these multiple connections in between the different branches. So I have put this in this extra file here, and we'll just be using the calculate receptor field function, giving it a Keras model, and it will tell us the receptor field, which is 184. So even though we have input sizes of 268, For the prediction of a single output pixel, the network will only see a window of 184 pixels. So that's just something you need to be aware of when creating these architectures. One last point I wanted to make here is about valid input sizes. So I've just told you that you can input any size you like. And in fact, that is actually true. However, if we want to, again, create these seamless predictions of very large images, we need to be very careful that pixels at the border of an input image are not discarded or treated any differently than pixels inside the image. And thus, for example, if you have a pooling layer, you should always give it an even input size. Otherwise, if it's uneven, this last pixel at the border of the image is something different happens to it. And we have this suggest input sizes function also from the receptive field.py script, which will do that. Given a model and a desired input size, it'll give us the valid input and output sizes. And we see here, now the reason becomes apparent why I chose 268, because it's a valid input size to this architecture that I defined. Okay, so enough about the architecture. Now let's move on to doing the actual training. So down here, I have defined a training function, which gets as input the training and validation data sets that we loaded earlier. And the first thing we need to do is we need to crop the labels, the ground truth labels, to the shape of the output size of the model. Otherwise, you can't really compare it if they're different shapes. So that's what we're doing here. And then I'm using this image data generator, which is a nice handy class of Keras. This can also enable you very easily to do, for example, data augmentation. I'm using it here to just center the mean and standard deviation of my data set, because it's always a good idea to give your models standardized data. So I'm just using that here. And we will see in a minute how I use that to fit the model actually. So this is just setting it up. And then down here, I create the optimizer. I'm using stochastic gradient descent here. You're also welcome to try Adam, for example, and see if that works better or worse. And now comes the training of the model. So now I'm using not the fit function, but the fit generator function of Keras. And this gets as input the result of data generator.flow, which is an iterator. And the iterator returns always nice batches of our training images and labels. And then in addition to that, we need to tell the network how many steps, so how many iterations of this iterator it should do per epoch, and the number of epochs we want to train on, and I give it separately the validation data. So I don't set just a validation split percentage, but I really give it the different validation data set. The reason here is that I sampled this validation data to come from different sections than the training data. So it's a bit more independent. In the last step, we'll just save the model. So let's execute that cell. And now let's go ahead with the training of the model. Wait, I'm on my notebook, so not a good idea to train the model because I only have a CPU. We will talk about this, and then I will just show you the data I've previously computed. So for the training, we can use learning rate of 0.01, 10 epochs, batch size of 24, and save the model out in this file here. So let me stop the computation. Hopefully that works. Yes, so go down here. So now, in order to execute all the rest of the notebook, I have thankfully prepared a pre-computed models folder, which contains all the results that I previously got for just such a case here. So if we execute this cell, we can ideally plot the history of the training. That is, we can plot the accuracy and the loss versus the epochs. So we can see here that what I previously did actually quite well, except this one peak here in the validation data set where something happened in the training, but it got back to training normally. In the end here, also the accuracy is rising. It's like a bit more than 80%. So that looks quite okay. So let's have a look at how this evaluates actually. And for the evaluation of these images, you have two choices. Either your large image will fit in the GPU, then you're fine, you can just predict it all at once. Otherwise, what you need to do is you need to cut this image in smaller, more manageable patches and predict those. And these patches, of course, need to slightly overlap because the output size of the network is a bit smaller, and we don't want to have any gaps in our segmentation in the end. So what I'm first doing here is I'm recreating the model with a slightly larger input shape, but it's not as large as fitting the entire image, because that wouldn't fit on my hypothetical GPU that I have here. So I'm uncommenting this line to actually load the weights I saved previously here. And we're calling the unit function again now with a larger sized input tensor, and then just loading the weights here. And then for doing the actual prediction, I have these three helper functions here, which first will create a grid of coordinates on the image, then we'll sample patches from these coordinates, and then we'll kind of do the reverse, that is, put the patches back together into a larger image, given patches, coordinates, and an output image shape. So let's define these functions, and then let's have a look at what they actually do. So I'm loading here an image from the test folder. I'm creating the grid, and I'm sampling from the grid points. So the grid is laid over the histological image like this. And then the patches that I extracted from each of these grid points are visualized down here. And you can kind of see that they're slightly overlapping as well. Now I would ideally execute this cell to predict the patches using the predict generator function of Keras, which again takes the data generator as an input. I need to use that data generator now because the network now expects inputs that are that are standardized. So I need to do that during the prediction as well. And note here that I put shuffle to false because by default this data generator shuffles your data, which is very useful for training, but not so much if you depend on the order of the outputs to put it back together into a larger image. So let's hypothetically execute this cell here and then just load the results that I previously got to visualize it. And what we can see here is, so this is the image, that's the ground truth labels, and that's the prediction I got from the network. Does it make that large a bit, right? Yeah. Okay, so we can see, so it kind of got the idea that cortex is on the outside of the brain and white matter is on the inside. It's not performing very well right now, but that's not surprising given that I only trained it for 10 epochs and with only these 500 sampling patches, training patches. And what additionally happens is that we have these misclassifications in the cerebellum down here, where parts of the cerebellum are classified as white matter. That's also not very surprising because they have very, very similar gray values to the white matter in the cerebrum here. And the receptive field of the network is not large enough to actually pick up on the fact that we are in the cerebellum here. So what we would need to do in order to fix this is to either increase the receptive field of the network, or for example, to input, like, for example, low resolution context as a second input in the network. You could also easily train for longer, decay the learning rate, or like increase the number of training patches, or use something like data augmentation. That should all help in this case to get the performance even better. How am I doing time-wise? Okay, 10 minutes, great. So we are not going to further trying to be improving the performance of this model here. However, I would like to go and quickly show you something about segmenting V1 because that's a bit more involved and there is some challenges down that way too. So I have prepared this V1 data set here. Now we have only two classes. We have V1 and everything else. And I have prepared it in such a way that the V1 class and the everything else class, the background class, are represented evenly in the data set as well. For training the model, I am now creating a unit with only 2 classes, because we only have V1 and the everything else / background class. Again, with the same parameters I trained the gray-white meta segmentation on, so I'm not going to execute that. But what we can do is load what I previously computed and see that the accuracies seem to be quite high, so that seems to have done something. But let's have a look at how the actual predictions look like. So to evaluate the model, again, I've now defined this predict image function, which does all of the create a grid of coordinates, sample the patches, predict the patches, and put the patches back together in the large image. It does all of that. And then I, again, recreating the unit with a larger input shape, again, with 2 classes. Here I'm loading the model. Oh yeah, I should comment this in if I were to execute that cell, which I'm not, because even predicting is going to take a bit too long on the CPU I'm on here. And then we predict the image and get out the resulting predictions. So if we have a look at what I did earlier, then we can hopefully see soon. Yeah, so we can see, oh yeah, the ground truth labels are not loaded yet, but that doesn't really matter, because what we see here is that instead of predicting V1, we kind of learned cortex segmentation, which is what we didn't want to do here. And there is several reasons for this. Compared to white matter and background, V1 looks quite similar to other cortex, because it's cortex, right? And the model sees an even distribution of samples from V1 and from other things in the image. But these other things contain mostly background, cerebellum, white matter, and maybe a bit of other cortex. And thus, it's very easy and very convenient for the model to just learn that whatever is in the first class is just cortex, and whatever is in the second class is everything else, which is exactly what it did here, and that actually gives us a high accuracy on the training sets, as you can see here, because they are sampled in such a way that both of these classes are represented evenly, and it performs quite well, but it doesn't really do what we wanted to do. So in order to fix that, what we really have to do is we have to split the background class into its distinct components and then train a network on 4 different classes. So train it on segment V1, other cortex, white matter, and background. And then if we sample evenly from all of these 4 classes, the network really should have an incentive to learn to distinguish between other cortex and V1, which it had previously difficulties with. So this is what I created this 3rd data set here for, and I used the gray-white meta segmentation that I had available already from the previous task. So if we have a look at these images here, you can see that that we now have 4 classes that are kind of a combination of the V1 labels and of the gray-white meta segmentation labels, and then we can do the training again, now with 4 classes. That's the only change here. And if I execute that, I'm just going to scroll over it, and we have a look at how this does. We can see that after 10 epochs, the accuracy is kind of still rising. So we might want to continue the training, actually, to learn for a bit longer. So that's what I did in this next cell here. I just trained for 10 epochs more with the same parameters. If I do that, the accuracies here, they flatten a bit. So there's not really any improvement anymore, but that doesn't necessarily mean that we have finished training, but that maybe we should reduce the learning rate and continue the training for a bit more. So that's what happens in this next part here. I just halved the learning rate and continued the training for actually 40 epochs, because I was a bit cautious at that point that I really wanted to learn something. So doing that will give us an output curve like this, where actually the accuracies are rising again and are now on the training and on the validation, I think, a bit over 80%. And now that they're rising again, you might even want to halve the learning rate again and continue the training and so on, which I didn't do here, but I wanted to see what I have actually learned by now, so how the predictions look like. So here I'm just predicting all of these models that I saved previously from the different epochs. And if we have a look at the results, here they are, we can see now that after 10 epochs, it looks really bad, right? I mean, we have learned white matter, cortex, and background, which is what we did previously, but you haven't learned anything about V1 really here. In fact, it's putting the V1 label to all of the cortex. After 20 epochs, things are a bit more diverse, but it's not really clear what it's doing in the cortex. It's not really consistent. And only after 60 epochs, you can begin to see, I hope you can, oh yeah, you can see it here, that it consistently predicts V1 around where actually V1 is located on this section, and it doesn't predict so much of V1 around here. Of course, there's still a lot of errors, but we can see that we kind of got the correct idea, and that's due to the longer training and this even distribution of these 4 classes in the training data set. So what I did after training this is in fact going back and training the 2 classes model, trained on only on ground truth labels like this. And I trained it for 60 epochs as well, but I couldn't get it to learn anything about V1. So the even distribution of at least V1 of the V1 and other cortex class is really essential here to get the model to learn something. And of course, this is far from perfect. So you could, train the model for longer or train on more data. And yeah, you're also very welcome to visit my colleague Christian Schiffer at his poster T555 on Tuesday, where we'll be presenting more about our newest approaches for doing these kind of things. And there are still some more details that I haven't mentioned here in this overview. So for now, yeah, I hope you could take something away from this. I will have a look at what happened with my data right in the beginning. And yeah, if you have any questions, I'm happy to take them. Thank you.